Since he's the one that founded him. Take it away, Carl.
So today our distinguished guest speaker is Dr. Tuiwa Sambuntunyako, who's a postdoctoral fellow at the Kavli Institute for Particle Astrophysics and Cosmology at Stanford University. He received his undergraduate degree in physics from the University of Chicago and conducted his doctoral study on galaxy clusters at MIT. Now, using the Chandra X-ray Space Observatory and the Magellan Optical Telescopes in Chile, Dr. Sambuntunyako researches the star formation rates and extreme X-ray characteristics of distant galaxy clusters in order to improve our understanding of high-energy quasars and large gravitational bodies in the universe. Please give a warm welcome to Dr. Sambuntunyako.
Okay, now that the formal part go, now I can be informal now. Okay, can everyone hear me? Yes. Okay, so my name is Taviwat, and I'm a postdoc down the road at Stanford University. And I'm here to talk to you about astronomy and why I think astronomy is cool. At the end of the talk, I just want to convince you one thing. Astronomy is cool, and that's it. You don't have to learn anything else. That's just one thing I want to get out. Okay, so I start getting to the background of some of the students here, but I just want to see again. So who here is a freshman? No one. Oh. Okay, so who here is a sophomore? No, sophomore too. Okay, who here is junior? Okay, wow. So most of you guys are junior, and who here is a senior? Congrats, you guys are almost done. I guess you guys are done, right? Okay, so before I give a talk, before I start my actual talk, I have to introduce myself for a little bit. So if you have not noticed, my name is really long, and that's because I'm not from here. So my name is Taviwat, and I'm actually originally from Bangkok, Thailand. I moved here to the US in 2010, I think, and then I've been here for the past 10 years doing physics. Okay, so yeah, just like Carl said, I did my undergrad at Chicago and PhD at MIT. But the most important thing is that I also like hiking, board game, and making graphs. Okay, the last one sounds kind of weird, but there are many kinds of graphs, and those are cool. Okay, and I like hiking because when I moved to California, everyone likes hiking, so that's the first thing I put on the board because I'm now in California. Okay, so one more thing before I start. If you guys have any question, just say it because otherwise I have no idea whether you guys got it or not. Okay. I usually start my talk with a punchline, and here is the punchline. So here is chip 1911 plus 4455. The number is not important, it's just the position on the sky. And chips, if you pay attention, that's the first slide. It's cluster hiding in plain sight. And it's important because I found it. That's why it's important. No. So at this talk, I will spend the next 30 minutes trying to convince you why this galaxy is just not a normal galaxy and why is it important and it's really unique. Okay, so let's hope that I can convince you that. In this talk, I will talk about a lot about galaxy cluster. Okay, now people were like, okay, what a galaxy and what's a cluster? So before that, I just gonna talk about galaxy first. Let's go simple and let's go slow. Okay, when you think about galaxy, what do you think of? So those are galaxy. Do you know what galaxy that is? Yes, that's the Milky Way galaxy building from the ground. But if we actually go to space and look at the Milky Way, you can see that the Milky Way is not just half of the disk. It's actually the whole disk. And you can see the center of the Milky Way is where all the dust is. Okay, let me see again. Yeah, I'm not gonna try the pointer. Okay, so in the center is at the center here there. Okay, and here is Andromeda. So Andromeda is one of the nearest galaxy next to the Milky Way, and it's basically our bigger sibling because it's bigger. I mean, I would not say it better, but yes, it is bigger. And the difference between the spiral galaxy and the elliptical galaxy is that in the spiral galaxy, you can see all these spiral or these dust feature on the Andromeda galaxy, but at the elliptical galaxy, they just like a blob, like a really, really bright blob. And that means the star doesn't move in coherent motion. So in the spiral galaxy cases, the galaxy moves in a disk. But in the elliptical galaxy, the galaxy moves in any random direction. That way it doesn't form any feature and it does look like elliptical.
What's the nearest elliptical galaxy to?
Okay, good question. I think the biggest one is the M87, the one that we studied the black hole images a couple years ago. And there are a smaller one. Okay, so now that I tell you the two different kinds of galaxies, I just want to show you the scale. So the top left is the Earth, and then you can zoom into the solar system, zoom out to the solar system, and then the inner solar system, the outer solar system. When you zoom out all the way, you get the closest nearby star, like Proxima Centauri and all these other galaxy stars. And when you zoom out, you get the Milky Way galaxy in the center, and that's what I was just talking about. So that's just one galaxy. And if you zoom out, you can see that there is one galaxy is the Milky Way, and the next door galaxy is Andromeda. And we call that a local group because those are group of galaxies. Really interesting name. But if you focus on the little dot on the local group, you can see that there are little galaxies. So we call that satellite. And it's just that these are smaller galaxies living next to the big galaxy. Okay, I will not go into the universe and all other things because we're not talking about that in this talk. Okay, I already talked about that and then that. Okay, and then, here is the coolest picture that I can find on the internet. I think it's a dam, and at the arm length. Okay, and if you look at the eye of the president on the dam, you can see that there is that little square, and that is the size of the image that I will show you on the sky. So if you put your coin at the arm length and you look at the eye of the president on the coin, you actually see that number of galaxies on the sky in just that tiny small area. And that is a lot of galaxies. So these are, like, for example, these are bigger galaxies, and there are like smaller galaxies and even smaller galaxies. And there are a couple non-galaxy objects like that is a star, and those also a star. So those stars are inside our own galaxy, but everything else is not in our galaxy, but in other part of the universe. And with this image alone, we call it a Hubble ultra deep field. And by just this one image alone, we can actually learn about all the galaxies in the universe. And to do that, we just assume if every dot on the sky have this many galaxies, and then we multiply by the number of squares in the whole sky, then we get estimate of the number of galaxies in the entire universe. Is it correct or not? I mean, nobody knows. That's all we can do for now. Okay, so we actually count the number of galaxies in the image like this, and we got 10,000. And then when we multiply, we got 100,000 million galaxies in the universe. And that is galaxies. Okay, any question about galaxy? Okay, now we're gonna go back to the part that I skipped at the beginning. It's a galaxy cluster. So I was talking about a group before. A group of galaxies is a couple of galaxies together, and a galaxy cluster is a cluster of galaxies together. Okay, now I have a question. So what do you think is a typical size of a galaxy cluster? If I put a Milky Way as one, how big is a galaxy cluster? So for example, a galaxy group that I was talking about, a local group that have a Milky Way and Andromeda, is about 3 size of the galaxy of the Milky Way. Okay, so I'll give you 10 seconds to decide 5 times, 50 times, 500 times, 5,000 times, or 50,000 times. Okay. Yeah, you guys can discuss if you want, but okay. Okay, so I will count down to 3, and then everyone just put your finger up as a number that you think you want. Okay, 3, 2, 1, go. Okay, I see a lot of 5, 5, 4, 5, 4. I see a couple 3, couple 5, or 4, 5. Oh, 2. We have a 2 here, and then we have a 4 and a 5. Okay, that's good. Yeah. Oh, if you notice, astronomer, we don't care about significance, so basically everything is order of 10, because that's as good as we can count. And the answer is about 500. Okay. Yeah, so it is big. So imagine an object that have 50 or 500 galaxies together into one thing called galaxy cluster, but it's not that big. It's not 50 or 500, or it's not 5,000 or 50,000, but it's still really, really big. Okay, so that is what a galaxy cluster is. Okay, so let me show you the first galaxy cluster image in this talk. Okay, so here is a galaxy cluster. You can see a lot of elliptical galaxies, just like I showed at the beginning. And then you can see a lot of spiral galaxy, this blue thing here. Do you know what this is? Why is it curved like this in the image? Oh, it is not a comet. That would be cool. So it's called gravitational lensing. So those are really background galaxies that are so much further away compared to this galaxy, but the light actually got bent by the actual galaxy cluster in the front. So we have the background galaxy, we have a foreground galaxy cluster, and the light from the background galaxy got bended, and then that's why it's actually curved. And by studying the shape of this kind of galaxy, we actually measure the mass of the galaxy cluster, and that's how we get 500 solar mass, 500 mass of the Milky Way. Okay, let's do some vocabulary on this image. The first thing is the brightest cluster galaxy, the BCG. I will talk a lot about the BCG in this talk, and it just means the brightest one in the galaxy cluster. And the rest of the galaxy, we call them members because they are not the center. Yeah, that's the 2 vocab I have. Okay, I hope everyone is with me so far. Okay, so here is again a galaxy cluster, but here's the cool part. So if you look at the galaxy cluster image, it's not in optical, but in different wavelength, we actually see this blue faint extended emission surrounding the whole galaxy cluster. Like in every empty space between each galaxy in a galaxy cluster, that it is really, really hot gas. And it's so hot that its temperature is about 10 million Kelvin. So what is the surface of the sun? How hot is the surface of the sun? It's 6,000. So it's 1,000 times hotter than the surface of the sun, and it's just there in a galaxy cluster. Okay, so let me give you a scale. So we have a human. So how hot are you guys? Yep, 98 Fahrenheit or 300 Kelvin, exactly. And then what about the campfire? The campfire is about 1600 Fahrenheit or 1100 Kelvin. And then the sun, just like I said, is 6,000 Kelvin. And the hot gas is 10 to the 7 or 10 million Kelvin. Okay, let me put that on a graph because, like I said, I like graphs. Okay, so here is the spectrum of the whole electromagnetic wave. So when we say the word light, the observable light, it only happens to be in this range between like 200, 300 Kelvin to like 10,000 Kelvin, and then that's where the eye can see. If you below the red, we call them the infrared, because it's cooler than the optical light, and if it's hotter than the optical light, we call it ultraviolet. And so if we use the night goggle, like this guy, you can actually see that the human actually emit light, but not in optical, but in infrared. So if you have an infrared camera, you can actually see the people or the human or the living thing at night, because the actual of the living thing actually emit light. In the same way, the campfire is emit light. That's why we can see the campfire, and the sun also emit light, because the sun it emit light in the same wavelength that we can see. Okay, but the hot gas that I was talking about is emit light, but the gas is so hot that the light that is emit is in the X-ray and not in the optical or infrared. So we cannot use the normal telescope that we use, like the Hubble Space Telescope or even the James Webb Space Telescope, to see a hot gas, because it happens to be in the X-ray. Okay, so that was I want to keep you. I want to keep in mind that the X-ray is hot and it's really hard to see. Okay. Back to the. Okay, so now why is the X-ray image actually interesting? If it just looks like a bulb, right, it's not that interesting. But actually, if you look at different kind of galaxy cluster in the same wavelength in X-ray, you can actually study a lot about galaxy cluster. So, like for example, this guy. You can see that there is this big cavity in the bottom and of the bottom and the top of a galaxy cluster. And then that when we learn that there is a jet coming out of the center of the galaxy and create this big bubble that you can actually observe in the X-ray. And that one on the top, the actual galaxy cluster moving so fast that it looks like a bullet shape. And you can actually see the shape by just looking at the X-ray image. Those ones also have the same bubble cavity, but there are not just two, but like multiple cavities. And then this last one is just sloshing. So like when you, in the morning, drink coffee, you try to stir a cup, you basically see the same structure, like this spiral shape here. That just look like the same thing. But this is on a much bigger scale and a much hotter temperature than your cup of coffee in the morning. Okay, so where does the X-ray light come from? So this is a very simplified version. So there are a lot of particles, and each particle are moving very fast because of the energy from the galaxy cluster. And when the particle moving really fast, it radiates out energy in the X-ray. Okay, and then as this particle radiates out energy, it actually will slowly cool down its own temperature. So we call them the gas start to cooling down. So the start is cooling from 10 to the 7 Kelvin all the way to 10 to the 5 Kelvin, and then all the way to where we can see in optical. Okay, let me simplify even more. Okay, everyone ski here? You guys ski here? Okay. Wow, there's a lot of people who ski here. Okay, so imagine if you guys are skier, and then if you are on the top of a hill. If you have 10 ski person at the top of 10 skier on the top of the hill, one would expect that all the 10 skier will come all the way down to the hill. The same thing with the galaxy cluster. If you see a lot of hot gas at high temperature, if we know that all the gas actually cool down, that means all the gas should eventually come all the way down to where we can see in optical at 6,000 or 7,000 Kelvin. So we're hoping that every time we see this hot gas, and then we count how much hot gas there are, then we can expect to see the same amount of hot gas at the low temperature as the gas cooling down. Okay, so basically in the picture of the galaxy cluster, then the gas will start to fall and start to falling in the center. And as it's falling into the center, the temperature of the gas will change into more hotter, like the X-ray, all the way to the red. Okay, So, okay, but if that's the story, I'm not going to be here because that's not interesting. But what happened is, in the galaxy cluster case, if we have 10 galaxies here on the top of the hills, only one galaxy actually found at the bottom of the hill. Now the question is, what happened to the 9 galaxies here? Skier, what happened to all this hot gas? Where did it go? And since it is a problem, we like to name everything. So we name them a cooling flow problem because they are cooling and we don't see it. So we name him a cooling flow problem. Okay. Anyone have an idea of what is the solution? Okay. One possible solution is just there has to be a really, really strong wind all the way at the galaxy skier coming down the hill, and this strong wind actually pushed the skier and they could not come down the hill. They just stuck up to the top. And that's why only a few of the skiers actually come down the hill. The same way in galaxy cluster, it's the same solution. We say that it's a really, really strong wind coming from the center of the galaxy cluster that push up all the gas to the higher temperature. Okay, let's do a little bit of simplified image that you can have in mind. So as the galaxy starts to cool, it will clump into a smaller clump, and those clumps typically will fall into the center. But because when it falls into the center, it actually activates the black hole inside the BCG or the brightest cluster galaxy. And when it activates the BCG, you can see the accretion disk, just like the black hole image that happened last week. And then that will actually create a whole lot of wind, and that wind will stop the gas to cool from cooling. And then that's why we actually don't see a lot of cool gas in the center of the galaxy cluster, and only very hot gas that we can see right now. Okay. Okay, is that everyone good? Good, okay. Okay, and eventually the black hole stops cooling, and then it just turns into a normal black hole. And then we call that a AGN feedback, because AGN just means an active black hole. And it means the active black hole that give a feedback. Okay, so now everyone asks, okay, how did you guys come up with this solution? Is it that obvious? It's not obvious. We spent a lot of time learning and trying to find a solution from why this is the case. And here is how good the best evidence that we show. So the blue in the two images here is the same X-ray image. And you can see the big cavity just like I showed you in the previous slide. But now we actually put the different wavelength in the red color, and that is the radio. If you study the radio, you can see one of the very important emission in the radio is a jet or a very powerful energetic event that coming from the center of the galaxy. And you can see that the jet from the central galaxy is so big that they actually cover the whole thing of the galaxy cluster. And that jet actually what creates the wind, and that the wind is what stops the gas to cool down. Okay, so that is the evidence and the solution for the problem. Everyone good with the solution? Does that make sense? Until. Back to our first galaxy cluster that I showed you at the beginning is, again, CHIPS 1911 plus 4455, and it's shortened from cluster hiding in plain sight. Okay, so here the image of a galaxy cluster, but in all the images that I showed you before, we use a really good Hubble Space Telescope. This one, I just use a telescope on the ground, and that's the best I can get. The center white blob there in the center is a BCG, just like the other BCG that we have. And all these smudge, and like those smudge or these, they are members. But I mean, you can barely see it in the image here. That's why we call some help. And then we actually got the same image, but with the Hubble Space Telescope, and we actually see that all those smudges is actually a member galaxy that are elliptical and red in color. And now you can see the central galaxy much better. And that white blue blob in the center is actually a normal elliptical galaxy in red, but it has this the cooling flow that we are trying to look for in all other galaxy clusters, and those are in white. So the cooling flow that we thought is a problem because we don't see any in most galaxy clusters actually is found here. Okay. Back to the analogy. If we have 10 skiers, in this case, we actually see 8 or 9 skiers down the hill. Now the question becomes, what happened to the wind? Because in almost every galaxy cluster, there is this strong wind coming from the center of the black hole that stops all the gas from cooling. But in this case, we don't see it. And that's what I got when I finished my PhD. So I don't have the answer after that yet. I'm still working on it. But okay, so that was, so that took me a while. Okay, so back again. So here is the same chip 1911. And then now we can overlay the same X-ray image that we have from the hot gas. And now you can see that this hot gas is a little bit different. Okay, let me just call them. Okay, the optical image is from Hubble and the X-ray image is from Chandra. But if you look at this X-ray hot gas, you can see that it's not symmetric. It's instead of a spherical shape that look like symmetric everywhere, it's actually asymmetric. So that means there has to be something going on with this galaxy cluster. Let me give you a little bit more. So on the left-hand side is the X-ray. Okay, so I forgot to mention, KPC is kiloparsec. So that means it's 100,000 parsec. And 1 parsec is 3 light years. So then you can multiply to get how big the galaxy cluster is. And you can see that the peak of the galaxy cluster, that's where the contour is at the peak of 2 circles. That is not in the center of the galaxy cluster. So we're saying that the galaxy cluster is dynamically active or asymmetric. And then if you look at the peak of the X-ray, you can actually see that the peak of the X-ray is coincide with the actual blue blob in the center of the galaxy in the optical. So that means the really, really hot gas that is at the center of the X-ray should be related to the cooling of the gas that we see in optical. Okay, so what am I doing now? So right now, so I'm getting more data basically. So we asking for 3.5 more days of data on the X-ray telescope to be able to actually get a much better image than this. Like this image is like 10 times less amount of data that we need. And then we're hoping to get a much better image in the X-ray and actually see what is going on in the center of this galaxy cluster.
Does your data just get transmitted down to Earth?
Yes.
Retrieve the satellites?
Yeah, so the data will come down to Earth maybe like once every 3 weeks or something. So it's a downlink from the satellite. Exactly. Okay. Yeah, so Chandra is one of the biggest telescopes that NASA built. It's actually launched in 2000. I don't know, are you guys 2000 or not born yet? Oh, never mind. Okay. So this telescope come after the Hubble, maybe 10 years. So Hubble is 1991, 1992. And then this one is 2000. And then it's the same one that's still using today because we don't have the better one yet. And yeah, it's still working fine.
You ask them to go look at something, and then who decides who gets to look with Chandra?
So there is we call it a proposal period. So every year, the telescope will ask all the scientists around the US and around the world who have a target that they think is important to study. And then they will like, okay, we have this amount of time in the whole year, like how much time we have. And then they allocate the time for each scientist, like how much time you get for each one. And then the best thing is once you get the data, you actually got the funding to work with the data. So then you can actually fund yourself, work on the project for a couple of years. Okay, so here is this is my last slide. So what did we learn today? we learned that astronomy is cool. Okay, hopefully. We learned that what a galaxy cluster is. We learned what an AGN feedback is and what the cooling happening. And then I just have to say we learned about chips 1911. Okay, and I think that's it. It's my last slide. Okay, thank you. Okay, now is a question and answer time. If anyone have questions, please let me. Okay, go ahead. So you have.
How much of the Andromeda galaxy do we know?
How many galaxies?
How much of the Andromeda galaxy do we know?
Oh, I mean, we know the mass, we know the size, but we don't actually know a lot about like the property and what the stars are like in Andromeda, because it's still really hard to study other stars inside of other galaxies. Okay. Anyone else? Yeah, go ahead.
What sorts of particles and chemicals are stars made of?
So there are different kinds of stars. The star that the sun is mostly hydrogen and helium, and then that's where the nuclear fusion comes from. And then the core of the star mostly have an iron core, and then there's a shell of carbon and nitrogen and oxygen, and those are where the core is. So, but back in the old time, like really long time ago, when the Big Bang started, it only have hydrogen and helium, because when the universe expanding at the beginning, it only have hydrogen and helium and doesn't have all these other core matter. So the first generation of star is called it only have hydrogen and helium, but those stars are all gone by now. And by the time that all those stars are gone, it actually produce a lot of heavy metal like iron and oxygen, and those are what form the star like our sun and what form the earth like our earth. Thank you. Go ahead.
Will you ever photograph directly the black hole at the center of the chips?
Okay, so in the past couple of weeks, we have image of the black hole in our own Milky Way and M87, but basically that's the only tool we can do right now, because the resolution, so this galaxy cluster, or this galaxy specifically is much further away, and the size is not big enough that you can actually see the actual image of the black hole by the same technique. So we have to come up with a new technique or try something else. Okay, you go ahead.
Do you think there are aliens?
I mean, personally, I think there is alien, because I mean there's so many stars, and then we actually learned recently from the Kepler Space Telescope that more than 50% of all the stars in the sky have planets. So I just tell you how much galaxies are there in the universe, and each galaxy have 100,000 stars, and 50% of those stars have planets. I mean, it's very hard to imagine one of those stars doesn't have a life. But yes, good question. Go ahead. Yeah, go ahead.
By taking pictures of these stars, aren't you looking back hundreds of thousands of years? It's not up to our time, right?
Yes, exactly. So this galaxy specifically is about 100 million light years away. So that means the image that we're taking is happened 100 million light years ago, because the light just got to us. Yes, exactly. Go ahead.
What is your favorite part about being an astrophysicist?
Good question. Okay, so I actually I don't like physics when I started my in high school.
I don't like.
But
I'm just kidding. I haven't taken physics.
Oh, okay.
I don't love physics.
Okay, so but I only like looking at stars and doing stargazing. So there are a lot of stars and constellations. So if you go to the night sky, you can see that each star on the night sky actually have different color, and different color stars give you a lot of information about what kind of star they are. But then my physics teacher in high school told me that I need to know physics to learn astronomy, so then I became a physics major. I mean, yes. So okay, that was not the answer of what you're looking for. The most important thing that I like about astronomy is that it's a very collaborative field, and also you get to go to cool places to take a picture of star. So like the image, the picture of the star here, we have to go all the way to Chile and take the image of the galaxy because the telescope that we use is in Chile. So there's a lot of traveling and also a lot of places that cool sites that you can get to see. Okay. Okay, go ahead.
How long would it take on like a spaceship to get to like one of these stars?
Okay, with our current technology, it's way too long because it takes the light 100 million years to get there, and our rocket and our spaceship could not go as even 0.1 speed of light. But if we have some other technique like wormhole and all these other technology, it could get there faster, but it's still in the theory. We don't actually know it yet. Okay, go ahead.
How long until you think we have the technology to be able to travel to like these galaxies?
Okay, I don't think I have to stop being an astronomer and become astrology now and try to actually I don't know. Probably not our lifetime. I think in our lifetime, Mars is probably the first place we get to go, and then maybe Jupiter or some other places. But I think probably it's gonna be a long time. Hopefully somebody else will do it. Okay. Anyone? Okay, go ahead.
You talked about the telescopes and they seem pretty old. Are they building like a new one right now, or is there?
So the new space telescope that just launched called James Webb Space Telescope, it actually just launched on the Christmas morning last year, and it's actually just got to where it is supposed to be like a couple of weeks ago. And that one is a telescope that only observes in the infrared. So the light that are cooler than the optical light, and that because when you study the galaxy, really far away galaxy, there is this Doppler effect because if as the galaxy is moving away from us, the light that is traveling, it actually got shifted to the redder and redder color. So if you want to study the first galaxy, the first star, the first black hole, or the first anything, you need to go to infrared. And that's why the next telescope that we're using is the infrared telescope. Speaking of the X-ray telescope like Chandra, we don't have a new one right now, but there are a lot of proposals for a new next generation X-ray telescope. But they are in still planning and building phase. So hopefully it will happen because I need it for my research. Go ahead.
How do you like take a picture of like a black hole?
Okay. You mean the one recently? Okay. So when we taking the reason that the Hubble Space Telescope and the telescope on the ground see very different things is because there is no atmosphere. Because when in space, but the resolution is about the same, but that's not the problem with the black hole. Because the black hole is actually so small. I think if you read the news, it's basically if you put a donut on the moon, and then that's how big the black hole is that we try to image. So we need a really big telescope. It actually is so big that the telescope size estimated to actually be need to take a picture of the black hole is the size of the Earth itself. So you need a mirror the size of the Earth to actually take a picture of the black hole. Now everyone might ask, but we take a picture of the black hole, and we don't have the one Earth-size telescope. So how did we do it? Basically, we have smaller telescope in all places in the whole Earth, like in the US, in South Pole, in Chile, in the Europe, and all these other places around the world. And when you take a picture at the same time, and you get a really precise clock, you can bring all the data together in one place and combine the image and pretend that we have a telescope the size of the Earth. And that's how we take a picture of the black hole. But the problem that it takes so long to take one image is because you have to hope that every place in the whole Earth have to be sunny and not cloudy at the same time. So you need a lot of luck. I mean, they did it so. Okay. More question? Go ahead.
So what was more fun to go to the University of Chicago or to MIT?
Huh?
Which one did you like the most?
Oh, wow. Okay. Okay. So I like Chicago. Yeah. I like Chicago more because I'm not an engineer, and MIT had a technology in it, so most people do engineer. And when you at Chicago, you feel more like you the main people. When you're at MIT, you're not a engineer are more important.
I'm also going there.
Oh, nice. Congrats. Okay, more question? Okay, go ahead.
What kind of galaxy is the Milky Way with the black hole, the wind and stuff? Do we have that, or are we one of the ones where all the skiers go down the hill?
Very good question actually. So if you look at the image of the black hole that we took last week, we see this light image. I don't know, everyone see the image, right? Yeah. Okay. So the light that are coming around is not from the black hole, but it's from the disk around the black hole. And those are the material that are falling into the black hole and create this powerful jet. But in our own black hole, the material is so little that the jet doesn't create anymore. So the jet and the wind doesn't actually happen anymore in our own black hole. But we think that it happened in the past, but not right now. Okay. Go ahead.
Sorry, this made me think of a question. So you just mentioned the accretion disk and the jet. So do galaxies, I'm thinking about the power of the X-rays from these jets. How old do galaxies have to be before they can even have, do X-rays just wash all the way up to the edge of the black hole? Is there a certain age galaxies need to be even before you can have life in them?
You're asking when did the jet happen in the lifetime of the galaxy?
Yeah, like in a baby galaxy.
Yeah, so most smaller galaxy, we don't actually think that is this accretion disk because the size is not enough. So I think the first generation of the galaxy might not have the accretion disk. It probably have a black hole. But so I think eventually they will start to form and all these things happen afterward. But yeah. Thank you. Okay. I think that's all the questions. Thank you. Oh, okay. Yeah.
The activity or not?
I don't know whether we have time, but okay. I can try. But I try to fit it. Okay, so since I didn't expected that many questions, so I have some other thing to do because after the talk, so I can try to do it, but I don't think we can finish it. But it's still a cool activity. Okay, so we study about elliptical galaxy and spiral galaxy, and then we actually try to classify a galaxy in terms of different types. We call them elliptical, spiral. Bar spiral just means a spiral galaxy with a center bar in it. And then irregular just means everything else because we gave up and we call them irregular. Okay, in all these 12 images, 3 of them is elliptical, 3 of them is spiral, 3 of them is bar spiral, and 3 of them is irregular. Okay, so I guess I will split you guys into 4 groups. So you have first group, and then here in the middle, then these are the second group, and then these are the third group, and you got the last group. Okay, so the first group will try to identify elliptical galaxy, the second group will try to identify spiral galaxy, the third group will identify the bar spiral galaxy, and the fourth group will identify the irregular galaxy. Okay, I'll give you 1 minute to discuss and try to pick the 3 that you think it is. Okay, 20 more seconds. 20 more seconds. You guys should decide among the group. Okay, I think everyone got it. Okay, let's start from the back. The fourth group, what number do you think it is?
5, 7, and 11.
5, 7, 11. Okay, that's the third group.
3 and 4.
There's 3 of them.
Oh wait, what's the last one? 8.
Okay.
Or 10. JK, 10.
Okay, the second group. 1, 8, 12. The first group. 2, 6, 9. Okay. Okay, let's see. The first group is 2, yep, 6, 9. Yep, perfect. Okay, the second group is 1, 8, 12. Yep, perfect. And then the third group is 3, 8, and the last one is 10. Yep. Yeah, I mean, it's not, spiral and bar spiral is not super obvious. And then the last one is exactly 5, 7, and 11. Perfect. Okay, so, but that is the easy part. So, in the normally, what we do is, we actually have like this image, we don't actually have a zoom in image. So now you have to like actually look at these like tiny smash and try to decide what are these. What are these? So, in this case, we have the fourth category because when you see a spiral galaxy, that's not just a head-on but edge-on, then you cannot really tell whether it's a bar or a normal spiral galaxy or other type, so that's why we call uncertain. And then from that, you can actually study the property of the galaxy cluster because each one of these images will tell you the population of different kind of galaxy. And then that's how you learn the actual galaxy itself. Okay, here is the time that we're waiting for. I have homework. No, I'm kidding. Okay, so basically, if we looking at this image and try to count how many galaxies are there in a typical normal galaxy field and a galaxy cluster field, we will see the 2 different populations, and then that tells you the evolution of the galaxies. And I think that's it for my time. I'll just leave it there. And I actually don't know how many people will show up, so I already bring a couple more galaxy images in the front. If you guys want to take one, I have like 40. I'm not sure if we have enough for everyone, but please take one if you want one. And then the last one is we have a lot of public events. Since you guys are like super close to Stanford, we have a public event that we host pretty often, so you can see information on the slide there. And then so like for example, we have the black hole, the lunar eclipse recently that we happened, and then So if you get those, then you can actually come to our website and come to our event. But Oh.
Any of the deep fields that you're talking about, do you use computers to analyze these, or is it done by just human beings staring at them?
So the first generation, we use a lot of manual work because we still, right now we use more computer vision and machine learning to try to identify. But the problem is you actually need label data, so you actually know what are these supposed to be first. So the algorithm is still not very good. But we still try to improve. Okay. I have more. If you can, I'll try to. Yeah, I'll try to contact them and then I can bring more. Yeah, now I feel bad. I didn't bring enough.
That concludes our meeting today. Thank you very much for coming. I guess you can get back to your classes if you got all the papers that you wanted.
Yeah, thank you.